So for now, we have discussed function of form. So we discussed g of x as summation n equals to 0 to infinity x to the power n, and this was your 1 upon 1 minus x. So what we did was the following. We wrote our function g of x as summation n equals to 0 to infinity of cn x to the power n, where all c1s are 1. So now the goal is to be able to write your function f of x as n equals to 0 to infinity cn x minus a to the power n for some a. And this should be valid for all x minus a less than r. So you start with a function which has a power series representation like this. And this is equal for all x minus a less than r. So now the point is, or the question rather is, can we write down Cn in terms of function f? Okay. So let's look at that. So suppose I have my function f of x, which is c0 plus c1 x minus a plus c2 x minus a square plus c3 x minus a cube plus c4 x minus a to the power 4, and then keep on going. So now notice the following. What is f of a? So f of a will basically render all of these guys. These guys will become all 0 when you put a in them. So therefore we get f of a is equal to c0. Is equal to c0. So again, we are trying to find out all the coefficients now. So we got f of a equals to c0. Okay. Now we want to find out c1, right? So how do we go about that? So in this case, we can take derivative on both sides. So if we take f prime x, what do we get? We get c1 plus c2 times 2 times x minus a plus c3 times 3 times x minus a square, c4 times 4 times x minus a cube, and all the higher terms, these terms have x minus a in them as a factor, right? Okay. So these terms have x minus a in them as a factor. So c4 times 4 x minus a cube, and so on and so forth. So now if we want to find out c1, then simply substitute f prime of a in this. So we get this is going to be c1, right? Because the other terms will become 0 when you substitute a in them. So this is your f prime of a. Similarly, let's take the second derivative. So f double prime of x becomes, so this c1 will become 0. So we'll have c2 times 2 plus 3 c3 times 3 times 2 x minus a plus c4 4 times 3 times x minus a square dot dot dot. These terms have x minus a in them. So if you look at this guy, f double prime at a is going to be 2c2. This would mean c2 equals to f. Now instead of double prime, I'm going to write this notation, right? So have we found out a pattern? We are close, but not yet, right? Because let's look at the third derivative at x. So then this guy will disappear. You will have, so this will become 0, right? When you take the derivative, so this will become 3 times 2 times c3 plus c4 times 4 into 3 into 2 times x minus a dot dot dot. All these terms have x minus a in them. So we have equals to, when you put a, these terms will become 0 because they have x minus a in them. So you get 3 times 2 times c3. So this implies c3 equals to f3 of a divided by 3 times 2. That almost looks like 3 factorial. Let's verify that. So we have fourth derivative. So fourth derivative of this is going to be, again, in that case, this will become 0. You'll have c4 times 4 times 3 times 2 times 1, which is 4 factorial, plus c5, which have x minus, these terms have x minus a in them. So again, when you take, this implies f4 of a is going to be c4 times 4 factorial, or this gives us c4 equals to f4 of a divided by 4 factorial. So we can get that way. We have, now note that we can rearrange things. So this can be written as 2 is same as 2 factorial. This is same as 1 factorial. And this can be written as C0 is C0 divided by 0 factorial, because 0 factorial, since 0 factorial is 1. I can rearrange it to write it as F0 of A to have a short comprehensive notation. So F0 of A is same as F of A. So I can write now, this gives me, so if I collect these information, one, this information here, this information here, and this information here, and the previous one. So this divided by 0 factorial. So I can write Cn is going to be Fn of A divided by n factorial. So therefore, your f of x can be written, if you have a power series representation of function A in the interval of convergence x minus a, or x minus a less than r, and your f of x is written like this, then these Cn's are essentially given by the following formula. Fn a, so nth derivative of function at a divided by n factorial. Here we adopt the convention that 0 factorial is 1 and fn0x is f of x. This is used so that we can write it in the short form. So if a function f has a power series representation at a, this is how f of x should look like. Okay, so yeah, so this is how it will look like. Okay, all right. So, and this such a representation is called Taylor series of function at a. Now, when a is 0, if you put a equals to 0, then you call this Taylor series with a new name. It's called the Maclaurin series. Yeah, after the name of the inventor. So again, when you put x equals to, if you put a equals to 0, what will happen? Your a will become 0, as you see here, and x minus 0 becomes x to the n. So this is the Maclaurin series, right? So Maclaurin series is a special case of Taylor series. So let's look at few examples now on computation. So first, Maclaurin series is here. So we want to find out Maclaurin series of the following function. Yeah. So Maclaurin series is what? So again, recall this is a Taylor series with Taylor series with a equals to 0. Yeah, that's the best way to remember it. Yeah. So we have again recall. So f of x will be what? Summation n equals to 0 to infinity fn 0 divided by n factorial times x to the power n. This is your Maclaurin series. So let's compute Maclaurin series for the first function. So what we'll do is we have f of x, so a, we have f of x, we have, so let's compute n, we want to compute the nth derivative of this, and we want to compute nth derivative evaluated at 0. Yeah, so this is what we want to compute. So let's do this computation now. Okay, so when n is 0, what is your first derivative? So 0 derivative of function means the function itself, it is e to the x. And then what is the value when you put 0? You get e to the power 0, which is 1. Similarly, take first derivative, again it's e to the x. Second derivative, again it's e to the x. Third derivative, again it's e to the x. And what is fn? When you put 0, you get what? You get again e to the 0, which is 1, 1, 1, dot, dot, dot. So this is what we are going to get. So therefore, we get e to the x is summation n equals to 0 to infinity n factorial x to the n. And what is coming new from here is that all these fn zeros are what? These fn zeros are all 1. So we get 1 times this. Or we get e to the x is, or we get e to the x is equal to summation n equals to 0 to infinity x to the n upon n factorial. So now let's repeat the same game with cosine x. So again, we have f of x. So b, we want to find out Maclaurin series for cosine x. So b, we have f of x equals to cosine x. So again, let's try to compute for n. Okay, so let's have n, one column for n, another column for the derivative, and then we want to basically, so this is for n, this is for fn of x, and this will be fn evaluated at 0. So again, we have n is 0, the function will be as it is, so we'll get cosine x, we get, when you put 0, you get 1. Similarly, when you have first derivative will be minus sine x, and when you put, you get 0. Similarly, when you have 2, the derivative is minus cosine x, and we get, when you put 1, when you put x equals to 0, you get minus 1. Similarly, we have 3, when you take the third derivative, you get sine x, and when you put 0, you get 0. Similarly, fourth one, so let's see if there's some pattern, we are getting some patterns or not. So cosine x, again we get what? We get 1. So seems like after 5, the patterns are repeating. Yeah, so you see you got back again 2. So after 5, what will happen is this pattern will repeat all over again. So we'll get for 5, 6, 7, 8. So for 5, we'll get what? For 5, we get, again, we'll get, I'll write down 0. For 6, we will get, for 6, we will get -1. For 7, we'll get 0. And for 8, we'll get 1. Okay, so this is the process which keeps on repeating. So you can see that cosine x is going to be what? So you have summation. So you have C0 plus C1x. So we have basically, okay, we have the following. So we have cosine x. So we have summation. So what we have is we have, so note that it is, so cosine x, first of all, can be written as summation n equals to 0 to infinity fn of 0 x to the power n over n factorial. Now, so this can be written as f of 0 plus f1 prime of 0 times x over 1 factorial f2 of x divided by 2 factorial x squared, and so on and so forth. Now, when you substitute the values, you will see that the first one is 1, but this one, this part becomes what? All the odd ones are 0, and there is a sign alternating between minus plus minus. So you'll see that this is going to be minus 1 times x squared by 2 factorial. Then the third one is 0. You have minus plus x 1 times x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial, and so on, so forth. So you can see that this is going to be summation n equals to 0 to infinity x to the power 2n minus 1 to the power n divided by 2n factorial. Okay. Another way to do this problem properly is the following. So you can write down, so you can break the series into two parts. You can write the even numbers as what? Even numbers are is of form 2k, and odd is of form 2k plus 1. So you have x to the power, instead of n, I'm using k and 2k. So 2k, so I can write it as f of 2k 0 over 2k factorial x to the power 2k plus summation k equals to 0 to infinity f of 2k plus 1. So 2k derivative 0, 2k plus 1 factorial or x to the power 2k plus 1. So you're breaking into odd and even part, right? Every n can be written as either 2k or 2k plus 1. And if you want to go through all n, just keep changing all k and you'll get this. Now this part is what? This part is all, we saw that these parts are, all the odd ones are 0, right? All the odd ones are 0. So this is equal to 0. So we are left with what? We are left with summation k equals to 0 to infinity f of 2k over 2k factorial times x to the power 2k. Now note that 2k, even the even ones follow a certain pattern. So this can be written as 2k. You have what? Here you have 2 times 0. Here you have what? 2 times 1. Here you have 2 times 2. Here you have 2 times 3. Here you have 2 times 4. So note that you're getting 1. You're getting 1 if this is even. Yeah. You're getting -1 if this is odd. You're getting 1 if this is even. You're getting odd. You're getting -1 if this is odd. So if k is odd, how do you get -1? You can just write it as -1 to the power. So if you have 2k, it will be -1 to the power k then. So you can replace now f of 2k of 0 with -1 to the power k divided by 2k factorial x to the power 2k. So this is one of the way of looking at it from general perspective instead of picking each element separately and looking at the structure. So this is how it goes. Now, so this is how you find out the Taylor series at a equals to 0. So essentially we have found out Maclaurin series, which is Taylor series at 0. Now a few more terminologies. The idea is again, so your calculator uses Taylor series to do approximation for sine and cosine. So approximation would mean you will stop after a certain stage. So that means what? You are only computing, say, from 0 to k. Yeah. And that looks like a polynomial of degree n, right? So that is called nth degree Taylor polynomial. And all the computational devices, when they have to compute these things, they compute the nth degree of this. Now, of course, if you let n goes to infinity of Tn, you get the whole Taylor series, right? Because you're letting n go to infinity, so the summation will go to infinity. And what is the remainder? So if you basically use Taylor series, so if you have Taylor series and you want to approximate it by Taylor polynomial of degree n, you will of course get some remainder, right? So you can write your Tn, you can write your f of x as Taylor polynomial of degree n plus remainder term. And what is this remainder term? Of course, remainder term is nothing but f of x minus Tn of x. And this is your error term, right? Think about it. You are approximating your Taylor's, you are approximating your series or your function with a polynomial of degree n. Then this remainder is the difference between them, or it is an error term. So then what do we get out of this? So we get the following. We get that, first of all, limit as n goes to infinity of Rn is 0 for all x minus a less than r. So in this range, to leave it open, this is r. In this range, limit as n goes to infinity of Rn is 0. And then your function is equal to the sum of its Taylor series on interval a minus r, a plus r. Okay. So for example, we have e to the x equals to 1 plus x squared by 2 factorial dot dot dot, right? So e to the power 2.6, because this converges for all real numbers, you can see that this is going to be 2.6 plus 2.6 square by 2 factorial plus 2.6 cube by 3 factorial, so on. So if you approximate it by degree 3 polynomial, we have T3 of x here is going to be 1 plus x squared by 2 factorial plus x cubed by 3 factorial. So you see the connection between the degree and this number here. In that case, what is your R3? Your remainder is going to be e to the x minus T3 of x, which is going to be what? X to the 4 by 4 factorial, x to the 5 by 5 factorial, x to the 6 by 6 factorial, and so on. Now we want to argue the following, that can we have some kind of bound on remainder? So you're going to use Taylor polynomials to approximate your function, and then you're wondering what could be the bound on the error term, which is your Rn of x. if you're using a degree n polynomial. So for that, we have the bound on the size of remainder. So we have the following fact, which says the following. So we have, so first of all, we must prove that remainder then goes to infinity r and x equals to 0. So to do this, we have the following two facts, namely that fn of n plus 1 x, if it is less than equal to m for all x minus a less than d, so you're at a, this is a minus d, and you have a plus d. Suppose for all these points here, you have fn a plus 1 is less than equal to n, then the remainder is bounded by Rn of x is less than equal to m upon n plus 1 x minus a to the power n plus 1 for all x minus a less than equal to d, or for all x coming from this region here. Yeah, so coming from this region here. Okay. Now fact 2 is basically you have that limit as n goes to infinity x to the power n over n factorial is 0. That you can check using basically, you can check it using 1 upon 1 minus x is summation n equals to 0 to infinity x to the power n. So how do you check this? You can check this by looking at the convergence of e to the x. So we have the following two thing, and now we want to basically prove that, yeah, we want to prove the following, that e to the x is n equals to 0 to infinity x to the n upon n factorial. You may say, well, haven't we proved that already? We found out that this Taylor series, we found out Taylor series for e to the x, right? And we said, well, Taylor series for e to the x is this guy. So what are we trying to do here? We are trying to basically find what, try to show that the remainder in this term is what, is basically 0. So how do we go about it? So first one, f of x equals to e to the x, a equals to 0. So you want to show that the remainder is basically going to 0. So let's compute fn of x, which is e to the x for all n belonging to n. So we have Rn of x is less than equal to m times n plus 1 factorial absolute value of x minus 1 to the power n plus 1 where x minus a or x minus 0 is less than equal to d. Okay, so now we have what? So given d greater than 0, for any d, for any absolute value of x less than equal to d, we have e to the x is less than equal to e to the d. Why is that? Because it's decreasing. So we have fn plus 1 of x is going to be less than equal to what? M. So that is going to be less than equal to e to the d. So therefore, by Taylor inequality, we get Rn of x, which is f of x minus Tn of x. So Rn of x is basically bounded by less than equal to e to the d upon n plus 1 factorial x to the power n plus 1. And now notice that this is a fixed number, and this limit as is what? Goes to 0. Why? Since limit as n goes to infinity of x to the n upon n factorial is 0 for all x. So therefore we get what? As n goes to infinity, we get Rn of x goes to what is limit as n goes to infinity of f of x minus Tn of x, which is 0. So therefore, it means what? F of x equals to what? F of x equals to T of x, which is the Taylor series of x. So these are the objects you need to know how to, you need to be able to find out the Taylor series. Then you should be able to uh, find Taylor series. Then you should be able to find Taylor polynomials. You should be able to find bounds on Taylor, bounds on Taylor remainder. Okay, so these are the things you must know on how to go about for the Taylor series. So these are the certain power series representation which we have already seen, and so let's look at them. So this is simply geometric series. We have already said, we have already done this. You should try this at home. We have already done this one, and we have already done this one. Okay, so now let's look at the following problem. Find Maclaurin series of the following function. So now there are two ways. Either you compute fn of x. Now that is going to be complicated because you have product rule here, right? So every time you'll have product rule, and that will basically become more complicated. However, we can do it in the following format. So let's consider. So we have e to the x is summation n equals to 0 to infinity x to the power n over n factorial. So we'll build it out. So therefore, e to the power minus 3x is going to be summation n equals to 0 to infinity minus 3x to the power n divided by n factorial. And that is going to be summation n equals to 0 to infinity minus 1 to the power n, 3 to the power n, x to the power n divided by n factorial. So therefore, x squared e to the power minus 3x is going to be summation n equals to 0 to infinity minus 1 to the power n, 3 to the power n, x to the power n over n factorial, and you're multiplying x squared. So you're multiplying by x squared, and that basically x squared comes inside, bumps up the power of x to the n by 2. So you get x to the power n plus 2 over n factorial. Okay, so now let's look at B. So again, Maclaurin series. So A is 0 in these cases, right? So we have again sine x is summation n equals to 0 to infinity minus 1 to the power n x to the power 2n plus 1 divided by 2n plus 1 factorial. And what are we looking for? We are looking for sine of x squared. So we'll replace this by x squared. So therefore we get, this implies summation n equals to 0 to infinity. So this implies my sine of x squared, sine of x squared is summation n equals to 0 to infinity minus 1 to the power n. Instead of x, I have x squared, the whole power 2n plus 1 divided by 2n plus 1 factorial. And it's always a good idea to write down the proper powers of x. So when you multiply it out, become x to the power 4n plus 2 divided by 2n plus 1. Now let's look at C in the similar vein. So we have C as h of x upon 9 minus x squared. We have already seen this before, right? So we shall have, so we have, this is same as, so we have, take x common, you can also take 9 common, and then this becomes 1 upon 1 minus x squared by 9. We have already seen the expansion for this, so this is going to be x by 9 summation n equals to 0 to infinity x squared by 9 to the power n. This is going to be x by 9 summation n equals to 0 to infinity x to the power 2n divided by 9 to the power n. And when you bring it inside, you can bump up the power. So we get summation n equals to 0 to infinity x to the power 2n plus 1 divided by 9 to the power n plus 1. So now this helps us. So now let's try to see, find some of the following series. So now, until now, whatever we have done about series, we could see the convergence and divergence of such a series, but we were not able to find the sum. So let's look at the following. So if we expand this, this is 1 plus 2 by 1 factorial plus 2 square by 2 factorial plus 2 cube by 3 factorial, so on. And this looks like e square. Similarly, let's look at the following. Here we have, if you relate to what series does it looks like, if you look at this series, you can relate it to arctan of x. So in that case, the series will look like, so we have, this series is same as, so we know arctan of x. Arctan of x is summation n equals to 0 to infinity minus 1 to the power n x to the power 2n plus 1 divided by 2n plus 1. So essentially what you're putting here is, you're putting evaluate at x equals to 1, and when you evaluate at x equals to 1, we get arc tan of 1, which is actually pi by 4, is equal to your series n equals to 0 to infinity minus 1 to the power n. This will become 1, right? So 2n plus 1. So this is what the sum of this series is. Right. So pi by 4 is equal to, so it's an interesting fact that pi by 4 is actually equal to this series here. Right. So now let's use the series to evaluate this. So first of all, if I evaluate directly, what do I get? It's 0. When x goes to 0, I get 1 minus cos 0. Cos 0 is 1. 1 minus 1, 0. In the bottom, I get 1 plus 0 minus 1. So 0 or 0 form. So if I use by L'Hopital's rule, this is going to be limit as x goes to 0 of sine x over 1 minus e to the x. Then again, 0 or 0 form. So if I apply L'Hopital's rule again, I get limit as x goes to 0 cosine x over minus e to the minus x, and as x goes to infinity, so as x goes to 0, my bad, we get what? Cos 0 becomes 1. You have this, so you get minus 1. So this is what we should get if we use series to evaluate it. So let's see using series now. using series to evaluate this. So note that if you write it down, you have limit as x goes to 0. What is 1 minus cos x? So 1 minus, what is a cos x? If I want to write down cos x as series, so x squared by 2 factorial plus x to the 4 by 4 factorial plus x to the 6 by 6 factorial. My bad, this has to be minus sign, and the process continues. We have 1 plus x minus, what is e to the x series? 1 plus x plus x squared by 2 factorial plus x cubed by 3 factorial, and so on. So now this limit is going to be same as limit as x goes to 0. So now I can cancel these guys off, and I can take minus x squared common from the top. So let me keep the minus sign outside. I have x squared common. What is left in the bracket? I'm left with minus 1 by 2 factorial plus x squared by 4 factorial minus x to the power 4 by 6 factorial, so on. What do I get in denominator? So 1 plus x will cancel. I have minus, I can take x squared common. I get what? I get 1. So this gets away. We get 1 upon 2 factorial plus x upon 3 factorial, and so on and so forth. Now we cancel these factors off. And now when you let x go to 0, everything will become 0 except for 1 by 2 factorial on top with a minus sign divided by 1 by 2 factorial with a minus sign. So these will cancel out to give you minus 1, which is what we got here. Yeah. So this is how we can use series to evaluate it. All right. So let's move to the next part. So here we are evaluating the Taylor series for the given value of A. So we have the following. So we have, for the first one, we need to compute. So let's see. So I have, okay. So we have n equals to 0, 1, 2, 3, 4. We want to look at fn of x, and then we want to evaluate at what point? We want to evaluate fn at 1 because your a is 1. So we are doing problem 1. Okay. Oops. So first derivative, so 0 derivative is the function itself, and the derivative will be e to the minus 1. If you take the second derivative, sorry, first derivative, then we get e to the power minus x, we get e to the power minus 1. Second derivative is e to the power minus x again, minus 1. Third derivative is minus e to the minus x, and then it will be e to the power minus 1 with a minus sign. So we get fourth derivative is e to the minus x, and we get again e to the power minus 1. So now from here we should be able to make pattern for nth derivative. So n, it is going to be e to the power minus x, but there is a plus or minus sign based on whether this is odd or even, right? This is odd, you have minus sign. If this is even, you have plus sign. So minus 1 to the power n. And this will become minus 1 to the power n e to the power minus 1. So this is your fnth derivative. So therefore, e to the power minus x is going to be summation n equals to 0 to infinity. How will the Taylor series look like? It will be fn at 1 divided by n factorial x minus 1 to the power n summation n equals to 0 to infinity. So in this case, it's going to be, we found that out, it's going to be minus 1 to the power n e to the power minus 1 x minus 1 to the power n divided by n factorial. So this is your Taylor series for your function. Now let's look at problem B. We have g of x equals to sine 2x and a is pi. So now we have to compute some derivatives. So n 0, 1, 2, 3, 4, 5, so on. And we need to compute the nth derivative. And then we need to compute the value of nth derivative at a, and your a is pi. So let's compute this. So what is the first derivative? So zero derivative is a function itself. And this is going to be sine of 2 pi, which is 0. First derivative is 2 cos 2x. And when you put pi, you get what? 2 cos 2 pi, which is 2. Similarly, when you take the next derivative, you have what? You have 2 square with a minus sign of sine 2x. And what is the value? You'll get minus 2 square times sine of 2. So it will become sine of 2 pi, again 0. So when you take 3, you get what? Derivative of sine is cosine. So minus 2 cube times cos of 2x. And when you put, you get 2 cube sine cos of 2 pi, which is minus 2 cube. Similarly, you have, this is going to be 2 to the power 4 sine of 2x, and then the answer becomes 2 to the 4 times sine of 2 pi. So sine of 2 pi, which is going to be 0. So we are getting the following. So sine of 2x, first of all, a is pi. So summation n equals to 0 to infinity fn of 0, sorry, fn of pi times x minus pi to the power n divided by n factorial. So we need to find out pattern in fn of pi. So note, what is fn of pi? So fn of pi is equal to, first of all, notice the following here. When you have n is 0, you get 0. N is 2, you get 0. N is 4, you get what? 0 again. So fn of pi is 0 if n is even. And let me finish this as well. So 2 to the power 5 cos of 2x, and this is going to be 2 to the 5 times cos of 2 pi, so that's going to be 2 to the power 5. And if n is odd, you're getting 2 to the n for sure, but you're getting this sign plus, you're getting plus, then you're getting minus, plus, minus, plus. So notice, what is the connection? The connection is, again, it depends again on your, so this is what, this is 2 times. So here, let's see the n. So n is, in this case, I have 2 times 0 plus 1. In this case, what do I have? I have 2 times what? 1 plus 1. In this case, I have 2 times 2 plus 1. So again, it is based on whether this k is odd or even. So if k is odd, you get minus sign. So it's going to be, how do I write it properly then? It's going to be plus or minus. So instead of writing f of 2, instead of fn, I should write f of 2k plus 1. Right. So it's 0 if, so what happens? Well, so f of 2k plus 1. So then in that case, note that fn of 2n is 0. 2n of pi is 0. And here we get fn of 2k pi is going to be minus 1 to the power k. So this is what we have figured it out. So let's see. So the sine 2x can be broken into two parts. Again, k equals to 0 to infinity, all the even parts. And then the odd parts. And now we know that this part is becoming 0, right? What are we left out with? We are left out with summation k equals to 0 to infinity minus 1 to the power k x minus pi to the power 2k plus 1 divided by 2k plus 1 factorial. And this is your formula for the function, the Taylor series formula. This is going to be, we forgot to add minus 1 to the power k, 2k plus 1. So this has to have x to the power, I should write minus 1 to the power k, 2 to the power 2k plus 1.